where the dion has magnetic charge M and electric charge N, which can be chosen to be coprime. And so we use electromagnetic duality to rotate to a frame where the dual charges are only electric. And in particular, the dual electric charge is 1. So this dion couples only electrically to some dual special coordinate. In particular, its mass is going to be equal to A prime. And since in this dual theory we just have it's just a U1 theory with a single massless hypermultiples of dual electric charge 1, we can use the formulas for the running coupling in this dual n equal to super QED, which just follows from the standard formula, and the free potential would look like this. So this again is just a one loop term plus corrections which look as follows. And essentially just by using this weak coupling, dual weakly coupled description, we can figure out the monodromy as we circle, as we loop around this singularity, and rotating back to the original frame, the monodromy matrix looks like this. So okay, I should stress here perhaps that, so here we have this Taylor series which corrects the log term. So this Taylor series is due to instantons. So here we also have a Taylor series which corrects the log term, but now the Taylor series is in A prime over lambda prime, and it's not due to instantons. I mean, in fact, this dual theory is just a U1 theory. So you should think of these corrections as coming from a tower infinitely many massive states that have been integrated out. So the picture that we want to, that we should keep in mind of the Coulomb branch is as follows. So the Coulomb branch is parameterized by U. So in particular, if we compactify it, say the Riemann sphere, and we have a singularity at infinity. In addition to this, we might have several other singularities, strongly coupled regions. Okay. So associated to each of these singularities, there is going to be some preferred weakly coupled variables that we use in our expansion, like here we use A, or here we use a dual coordinate A prime. And when you express everything in terms of these weakly coupled variables, we'll have some logarithmic terms, which are determined by the one loop running and are responsible for monodromies. And in addition, there would be some Taylor series, which are taking into account instanton corrections or corrections due to integrated out massive states. So in principle, what we want to find is, so first of all, to determine how many singularities there are, where they're located in, say, the U-plane here, and also what is the massless particle, which is the massless dion, which is responsible for that singularity. So that will tell us about these monodromy matrices, and in addition, we would like to determine all these coefficients in the Taylor series expansion. So, okay, so essentially, around each singularity, we'll have some expansion in some small expansion parameters. So the idea that you should keep in mind is that, say, you have some around each singularity, you'll have some description which holds in a patch, and we want to patch together these local descriptions in a globally consistent way. And okay, so the key idea is that patching together all these local informations in a globally consistent way will fix completely the infrared effective action. So what is this global consistency condition that we need to fix the problem? So this is a consistency condition on the monodromy group. Let's have me here erase a bit. Okay. So how do we compute the monodromies? So we start from say some base point u0, and then we consider loops around singularity. So we start by considering a loop around infinity, which we took oriented counterclockwise. Okay, so let's call this loop gamma infinity. On the other hand, we can compute the monodromies around various other singularities, like this. Let's call this gamma u1 associated to singularity at u1, singularity at u2, so this is gamma u2, etc. Up to singularity at un, gamma un. Okay, so now because you can deform this loop gamma infinity into, say, the union or the composition of all these loops, it follows that the monodromy matrix around infinity, M infinity, should agree with the products of the monodromy matrices that we get by following each of the loops. So M u1, M u2, up to un. So I should stress that here there is inherent in the definition of the monodromy, there is a choice of base point, and so here you might say pick a different base point, and so there is some reordering ambiguity of these monodromy matrices, but essentially this reordering ambiguity just acts by conjugation, so will not affect the physics. So let's pick one choice. So, and this is, so this, okay, so these loops, let me see. So the group of loops based at U0 is nothing but the fundamental group of the Coulomb branch. So you should think of this as the sphere with a number of punctures, so there are now some non-trivial loops which live in this group.
Sorry?
Yes. Okay, so I should have written this here. Sorry, let me copy again. Yes?
Is U0 a singular point?
No, here it's just a base point. I should have probably used a different name. So the singularities are just the dots, and this is just the choice of base point. Okay, so now let's go back to our original problem. So yesterday we excluded the possibility that in addition to infinity there was a single other singularity in the strongly coupled region. So now the next to simplest option is that there are two singularities at strong coupling. Okay, and recall that there is a Z2R symmetry which is broken on the moduli space. So this will be at say U0 and minus U0. And then since they live in a strongly coupled region and for dimensional analysis, they have to be proportional to lambda squared, where lambda is a strongly coupled region. And so essentially you can reabsorb any coefficient in your definition of lambda. And for, I don't know, later purposes that I will never reach, choose to have a factor of 2 there in front. Okay, never mind, and the 2 is not really important. And so, so what we're considering here is a situation where, well, maybe draw it then. So we have the U-plane, so say we pick, I'm using the same notation for many things, so this will be the singularity, so let's stick with the U0 for the base point here. And so we're going to have a singularity at -2 lambda squared. And very good. No, I'm not there yet. I asked for colored chalks. I went to buy them just for me. Okay, so here once again we have the loop at infinity, and we're going to have a loop gamma -2 lambda squared, and another loop gamma 2 lambda squared. And the consistency condition is that m infinity is equal to m minus plus 2 lambda squared and minus 2 lambda squared. And we interpret these two singularities as coming from massless solitons. So here m infinity is the monodromy matrix which I wrote there. And m plus or minus 2 lambda squared should take the form mn for some choices of magnetic and electric charges. Okay. So since I mean we have the expression for the monodromy matrix at infinity, we have the expression for the monodromy matrix due to a massless dion of charges m and n, and so you can impose this condition and try to solve for the magnetic and electric charges of the massless solitons at these 2 points, singular points in moduli space. And essentially the only solution up to conjugation, which does not in a way affect the physics, is as follows. So at 2 lambda squared, the monodromy matrix is m1, 0, so minus 1, 0, minus 1, 1, which is also equal to s to the minus 1, and this is associated to a massless monopole, because the object only carries magnetic charge. Whereas the one at -2 lambda squared is due to an object of magnetic charge 1 minus 2. And this is due to a massless dion. Of charges of magnetic charge 1 and electric charge -2. Okay, so I should maybe mention here that in the conventions that we're using for the charges of, and say in a fixed duality frame, the electric charges of the ions are even. So this is kind of a minimally charged dion. And okay, let me also mention that you can express this monodromy matrix in terms of P and S, and this is also equal to P squared m1, 0, T2 minus 2. So in particular, the two monodromy matrices associated to the two singularities at strong coupling are related by conjugation. And this is due to the fact that there was this Z2 R symmetry, which is broken on the vacuum, so the physics at point 2 lambda squared should be essentially the same as the physics at point -2 lambda squared. Okay. And so maybe yet another comment which is related to this Z2R symmetry, in fact, in a way that I will not explain, is that if you pick the other convention, the other ordering, so say instead of starting from base point u0, you start from a base point of minus u0, then you will reverse the order of these two monodromy matrices. And if you do that, then the dion here will have a magnetic charge 1 and electric charge plus 2. Okay, so the physics is going to be the same. So, okay, so if we just assume that there are two singularities in the strongly coupled region, there is a solution, so it seems, it looks like we're in business, but you might consider the possibility that maybe there are even more more singularities, and you can still solve a similar global consistency condition. So this is, in fact, some well-defined mathematical problem, and it has been shown under some mild assumption that, in fact, the only solution to the problem is to have just two singularities with this monodromy matrices associated to massless monopole and massless diamond. Okay, so before we go on and use this information to solve the problem of determining the infrared effective action of n equal 2 super Young means with gauge group SU2, so let me pause to consider a very interesting application to instead a system with n equal 1 supersymmetry, which again was pointed out by Seiberg and Witten. So so far we've considered a theory with n equal 2 supersymmetry, but you might consider softly breaking n equal 2 supersymmetry down to n equal 1. And how do you do that? You introduce a superpotential which gives mass, say, to the scalar phi, to the chiral superfield phi in the n equal 2 vector multiplied. Okay, so when you do that, you integrate out the massive scalar, and so you're just left with n equal 1 massless vector multiplied. So in particular, this breaks the classical SC2 R symmetry, C1 R symmetry of the n equal 2 theory to a single U1 new U1 R symmetry, which gives charge 1 to phi, so that the superpotential has charge 2. And this is broken by an anomaly to Z4. Okay. So classically, this superpotential gives mass to the complex scalar phi, which was taking expectation value on the Coulomb branch. And so you would expect that classically the Coulomb branch is lifted. And so if this was the Coulomb branch, say, essentially all points are going to be lifted except for the origin. So, say, I don't know, the potential will look like this. So only the origin remains as a vacuum. Okay. So now we would like to study the effect of these soft breaking terms in the low energy effective theory, taking into account quantum effects. So at least if the mass is small, you would expect that you can take this soft breaking term into account by adding an effective superpotential to the n equal 2 effective description that we used, which goes like mass times u, because u, remember, was the expectation value of half trace phi squared. Okay. So in fact, and then in fact, Seiberg and Witten argued using holomorphy that this is valid not only for small values of n, but for any values of M. So, okay, so let's first consider the situation where we are outside a singularity, let's say at a regular point in the Coulomb branch. The F term of the variable u in this superpotential is proportional to M, so it's non-zero. Okay. The scalar potential goes like, say, k u bar, where this is the inverse scalar metric fu bar. And if we're at a regular point, the scalar potential is it's regular, it can be inverted, and this is going to be positive. Okay. So this is a regular point in n equal to moduli space will be lifted by this softly breaking term. So on the other hand, if you are at a singular point, the scalar potential, the scalar metric is not invertible, so you might think that this goes to 0, and you can still have a vacuum, a supersymmetric vacuum, even though naively the F term is different from 0. Okay, so let's see what happens at the singular point by including the fields which, the extra fields which cause the singularity and become massless. So let's consider first the singularity at 2 lambda squared due to a massless monopole. Okay, so we start from we have the superpotential above, which came from a soft breaking term. And in addition, so we also have to add these massless monopoles, which couple linearly to the dual special coordinate. And so in particular, at this point, u equal to lambda squared, remember that so a dual equals to say C naught some constant times u minus 2 lambda squared, and this is the mass of the magnetic monopole. So we'll have a term, some mass term C naught u minus 2 lambda squared times m and twiddle, where m and twiddle are the n equal 1 chiral superfields in the monopole hypermultiplet. Okay. So next, we try to solve F-term equations for this superpotential. So if we differentiate the superpotential with respect to u, we get m plus C naught m tilde. If we differentiate the superpotential, the effective superpotential with respect to m, we get C naught u minus 2 lambda squared and twiddle. And if we differentiate the superpotential with respect to m tilde, we get C naught u minus 2 lambda squared m. Okay, so these are the F-term equations that we want to solve. And clearly, there is a simple solution now, say where u equals 2 lambda squared, so that we solve these two equations. This is the point where the monopole is massless. And so the monopole is massless, you can acquire expectation value, and we can then solve the next F-term equation by saying that m and twiddle is equal to minus m over C naught. So indeed, what we found is that the point u equal to lambda squared on the Coulomb branch, which corresponded to the singularity in the n equal to moduli space where the monopole is massless, survives when you softly break n equal to supersymmetry to n equal 1. And so it remains a vacuum in the n equal 1 low energy theory. And so you can essentially repeat the same analysis at the dion point by replacing monopole hypermultiplet by dion hypermultiplet and minus 2 lambda squared by minus 2 lambda squared. And so the picture that you find is as follows. So with n equal to supersymmetry, we had these two, we had a Coulomb branch of vacua, which looks like a complex plane, and we had these two singularities at plus and minus 2 lambda squared. So when you softly break to n equal 1, at a regular point in the moduli space, supersymmetry is broken, the potential is positive, but at one of the two singularities of the n equal 2 moduli space, you still have a supersymmetric vacuum. So say the picture will look like something like this. Right? Pictorially, so this minus 2 lambda squared and 2 lambda squared. So what we find is that there are two supersymmetric vacua which are pinned to the singularities of the n equal 2 moduli space. So, and this is a nice result because it was expected by other arguments that n equal 1 superior means with pH group SUN has precisely n vacua, which are related by broken R symmetry. So, for instance, one can compute the Witten index, and the Witten index is NC, so here 2 in this case. So it looks like we're getting a consistent picture. And the important point here is that, so let's focus again on the vacuum corresponding to a massless monopole, is that we have solved these F-term equations. And okay, so not only the scalar field in n equal to vector multiplet, which is massive, must take the value which corresponded to the singular point, but in addition, the magnetic monopole has to acquire expectation value. Okay, so this is what is referred to as monopole condensation. And similarly, at the other points, at this point, you have condensation of monopoles, and at the dion point, you have condensation of dyons. Okay, so if the monopole condense, so they're charged under the, they're magnetically charged, and so they will give rise to some magnetic X mechanism. And in particular, this implies that they will give rise to some magnetic version of the Meissner effect. So recall the Meissner effect of superconductivity. Okay, so essentially you're in a superconductive phase, and electric fields are confined to leaving some short, the flux. The magnetic fields are confined to live in a flux tube. But now, since we're, now in this case, it's the monopole which condenses. So we have a dual version of the Meissner effect, and so now these are electric flux tubes. So this is confinement for, let's say, the electric charge. So, in fact, precisely this kind of mechanism was first proposed by Tochter and then also by Mandelstam in the 70s as an explanation of confinement. So, confinement was thought to be due to monopole condensation through this magnetic Meissner effect. And so in this n equal 2 supersymmetric context, softly broken to n equal 1, one can find an explicit realization of that idea.
Sorry, Could you say exactly why? I mean, the softness of the breaking is related to the size of M, or to, I mean, when does this description breaks down?
Okay, so there are all sorts of issues about Taylor potentials and so on when you have N+1 supersymmetry. But okay, so first of all, you would agree that at least for small value of n is a good description. And then essentially Seiberg and Witten use some sort of holomorphy arguments to argue that at least if you focus on S terms, this description will hold for any value of m. Okay. It doesn't tell you anything about the Keller potential, but as long as say the Keller potential is non-singular, you can just look at F terms. Okay. Okay. So now we finally get into the solution of the problem. So now we go back to n equal to SC2 Seiberg Mills, no soft breaking to n equal 1. So we have our physics problem. Which is to determine the infrared effective action of n equal to pure SC2 Seiberg Mills. And we have translated this to a mathematical problem of finding multi-valued functions, say our special coordinates a dual and a, say as a function of u, the coordinate which parameterizing the Coulomb branch, or mathematically holomorphic flat S2Z section. Okay, so just think of this as multi-valued functions with prescribed monodromies. M infinity plus or minus 2 lambda square at singularities infinity and plus or minus 2 lambda square. Okay? With the precise monodromy matrices that we derived before. And in addition, we also would like to have by unitarity, so the complexified coupling tau of u, which was differential of a dual, derivative of a dual with respect to a. So we also want this object to have as positive imaginary part. Okay, this due to unitarity, because remember the metric, the Keller metric was essentially given by the imaginary part of tau. Okay, so this mathematical problem is in fact well-known and well-studied problem. It falls into the class of called Riemann-Hilbert problems, and it's known that it has essentially a unique solution up to multiplication of a and a dual by an entire function. Okay, yesterday I was caught off guard about the definition of entire function. So entire function, let me remind you, so these are holomorphic functions on the complex plane. So the radius of convergence is infinity, but they might have a pole at infinity. So think of a polynomial or an exponential. Okay, so multiplying a dual and a by the same entire function will not change the monodromy, and so clearly this is an ambiguity. But physically, we can fix this ambiguity by imposing the correct with coupling asymptotics. far away along the Coulomb branch. So in the region U goes to infinity. Okay. So now, since we have to deal with monodromies, let's pause for a few minutes and look at the monodromy group. So the monodromy group is generated by any two of these three monodromy matrices. And it turns out to be this group, which is a congruence delta. It's a subgroup of SL to Z, and it's a congruent subgroup where beta is 0 modulo 4. Okay. So if you take any two of these three monodromy matrices, that will generate precisely this group. So note that, so first of all, the S transformation does not belong to this monodromy group, essentially because this entry has to be 0 modulo 4. The T transformation also does not belong to gamma 0 mod 4. However, I guess T to the 4th can belong to gamma 0 mod 4. So this is some specific subgroup of SL to Z. So now, as U varies along the Coulomb branch, tau, the complexified coupling, will vary. Tau U varies in the upper half plane, which they call, I guess, H plus. But it's also subject to monodromies as we go around singularities in the U plane. Okay, so the monodromies again are in around singularities and gamma not 4. So this tells us that the Coulomb branch. Okay, so you essentially, so you should think of this upper half plane as some cover of the U plane, okay, where the cover is due to the fact that you might pick monodromies as you go around paths in the U plane. So we expect that the Coulomb branch is given by the upper half plane modulo the monodromy group, which is gamma naught divided by 4. So again, here the Coulomb branch is parameterized by U. This is the parameterized by tau of U up to the action of the monodromy group. So in the first lecture, I reminded you what is the fundamental domain of SL to Z. So now let's try to do the same exercise to understand what this right-hand side here is. Okay. So now the fundamental domain of this monodromy group, gamma naught of 4 is as follows. So again, let me plot this the tau plane. And okay, so tau lives in the upper half plane. Let me start using the color chart so the organizers will not complain. Okay, so as I told you, the T transformation, which is tau into tau plus 1, does not belong to the to this monodromy group, but on the other hand, T to the 4th, which is tau to tau plus 4, belongs to this group. And so, okay, so first of all, if this is -1, -2, 1 and 2, we can use the T transformation to go to this strip. And again, this edge here is identified to that edge. So here, say we have I infinity. And then, in fact, you can use one of the other generators of n infinities, for instance, the monodromy matrix due to 2 lambda square or minus 2 lambda square, to see, in fact, that the fundamental domain will look like this, where, in fact, this is the identification. So in fact, topologically, this space is again a sphere with 3 punctures. The 3 punctures correspond to the cusps, and okay, and the cusps here are tau equal I infinity, tau equals 0, this cusp here, and tau equal 2, which is also equivalent to minus 2. Okay, so now exercise. So first of all, you should be able to motivate this identification. So this line is identified with that line, and this half circle is identified with that circle. And the second part is of the exercise is to identify the cusps. As a fixed point of elements of this monodromy group. And associate, say, the cusp at tau equals 0 to a massless monopole of charge, magnetic charge 1, electric charge 0. So this will correspond to the point in the U-plane where U is equal to 2 lambda squared, so this cusp. Instead, say the cusp at tau equal 2 is associated to a massless dion 1 minus 2. This corresponds to other singular point in the strongly coupled region in the U-plane, minus 2 lambda squared. Or in fact, similarly, if you go to tau equal minus 2, you will find that the dion with charges 1, 2 is massless, but this is, corresponds to the same point. Well, and then obviously, tau equal I infinity corresponds to a weak coupling point that corresponds to having U at infinity. Okay, so now we've encountered this monodromy group, gamma 0, 4, and so we see that the Coulomb branch is isomorphic to the fundamental domain of this monodromy group. So now this monodromy group is a subgroup of SL2Z. Okay. And SL2Z is the group of large diffeomorphisms of the two torus, meaning so the group of diffeomorphisms up to equivalence classes of the diffeomorphisms which are connected continuously to the identity. So gamma 4 is SL2Z. So the two torus that we view as C2 divided by lattice Z plus tau Z. Okay. So say if we are here in a, so let me introduce another plane. Say 0, 1, tau. So this is the standard description of a two-torus by some, say, complex variable, sorry, C. Some complex variable up to this identification, or so we can take this to be 1 and the other one to be tau. So say this is the alpha cycle of the torus, and this is the beta cycle. And okay, we can go to the we can actually go to the covering space. And so here, for instance, well, let me also draw the torus in the usual donut shape. And this is alpha cycle. So here I'll take the convention, and this is the alpha cycle, and the beta cycle goes the other way. This. Okay. So tau is the complex structure modulus of the torus, or well, I guess if you generalize to Riemann surfaces of higher genus, it would be called the period matrix. And you have this SL to Z group, which leaves the lattice environment up to rescalings, and particularly the T transformation, as we saw, sends tau to tau plus 1, and so in particular it sends the beta and alpha cycles to beta plus alpha and alpha. Okay. So this is like you know, taking this as a new fundamental domain. And we also have the S transformation, which sends tau into -1 over tau, and this S transformation exchanges the beta and the alpha cycles. With these signs and my conventions. So if you consider any loop or any one cycle in the two torus, gamma in the two torus, so this will have winding numbers m and n, which will express how gamma is decomposed in terms of the basis of cycles given by alpha and beta. So I can show this, write this as m comma n beta alpha. Okay, so now you should start to see that this is so we are encountering here in the discussion of the torus a structure which is very similar to the one that we had before. In particular, so here we have homology cycles, say beta alpha, and this looks very similar to special coordinates A dual and A. And in particular, so here the winding numbers and n look very similar to the electric magnetic charges. So here on the torus you have some complex structure modulus, which is the period matrix. tau. And this looks very much like the complexified gauge coupling. So finally, for the two torus SL2Z, there are some large, sorry, for the two torus, there are some large isomorphisms which are SL2Cs. Which here we can in fact think of as changes of basis of cycles, beta and alpha, and also changes of winding numbers, so that the cycle itself is invariant, and this is looks very much like the SL2Z electric magnetic duality group. So since the structure on the physics side and the structure on the mathematical side look very similar, in fact kind of isomorphic up to, I have to explain what happens in the first line, what Seiberg and Witten did was to identify the two sides here. And okay, in a few minutes I'll tell you how the map goes for the first line. So on the physics side here, on the right hand side, the special coordinates and the complexified coupling varied along the Coulomb branch. Okay, so it had something like our Coulomb branch and Coulomb, and okay, on top of these two singularities, strong coupling and other singularity of fluid coupling. And on top of each point on the Coulomb branch, you have, say, a dual and a, so this is as a function of u. And in particular, that means you also have a tau effective complexified coupling as a function of u. So now, since tau is the complex structure parameter of the torus, what Seiberg and Witten said was, okay, so now we can in fact encode all this information on the physics side about the special coordinates in tau in terms of some auxiliary to torus, which is fibered over the complex plane. So here, instead of giving a dual and a, let's first declare that there is some two torus whose complex structure tau is gives the value of the complexified Yang-Mills coupling, complexified electric magnetic coupling. Okay. So and then in a few minutes, well, I guess after the break, we'll also see how, in fact, not just the complexified coupling, but the special coordinates will arise. Okay. So we have, say, one parameter family of tori. So following this idea, one parameter family of genus 1 Riemann surfaces. Which are isomorphic to the two torus, so which say varies holomorphically with U. Okay, the fact that it varies holomorphically is because of n equal to supersymmetry, and so we have in fact some bundle where the base is the Coulomb branch and the fiber is given by the torus, whose complex structure determines the value of the coupling. And we'll see that at singular points, what's going to happen is that one of the cycles will vanish, and that will lead to a singularity. For instance, this is what happens at the diamond point. So here the beta cycle. So here we have the beta cycle, which vanishes. So, alright, so we have this, so we want to have a one-parameter family of tori which vary holomorphically along the base. And we also, because the monodromy group was this group gamma 04, we also wanted the complex structure moduli space is exactly the upper half plane divided by gamma out comma 4, which is isomorphic to the Coulomb branch. Okay, so this might look a bit abstract, so I will be more concrete after the break. And so we'll construct this torus in terms of algebraic equations, and we will see it's one cycle, say the alpha cycle and the beta cycle. We'll study the singularities of the torus in the complex structure moduli space. We will see how the special coordinates are related to the homology cycles, and how the singularities associated to masses, monopole, and dyons arise on the mathematical side. Okay? So let's take a break and continue 5 minutes. So the idea, as I said, is to encode all this rigid special Keller geometry of the Coulomb branch of this SU2 gauge theory in terms of some auxiliary Riemann surface, in this case 2 torus, which is fibered over the Coulomb branch. And so we want one complex parameter family of 2 tori, where the complex parameter is u, the coordinate on the Coulomb branch, and such that the complex structure moduli space of this one parameter family is the fundamental domain of the monodromy group. So how do you do that explicitly? You describe the 2 torus as which depends parametrically on u in terms of some algebraic equation, which can take to be of this form. So this is usually called the Seiberg-Witten curve. Okay, so here curve is in the mathematical sense. So this is a complex manifold, and mathematicians call curve whatever has dimension 1. But this is complex dimension 1. So we will call it. They wouldn't say 2 torus typically, but we would call it elliptic curve. Okay, for that reason, this is called a curve. So this is one equation in y and x. So y and x are variables. So I determine, say, y as a function of x or x as a function of y, and u is a parameter. Okay, so this is one equation in x and y. Think of them as complex variables, and u as a parameter. Okay, so let's now try to see why these algebraic equations determines 2 torus. So in particular, since say, okay, well, we might view the curve in different ways. So I guess for today, what I'll just do is is to view this equation as determining y as a function of x. Okay, so let's rewrite this. The right hand side is a degree 4 polynomial, so it has 4 roots. Let's give a name to the 4 roots. Pi, which will be functions of u and lambda. Okay, so and the 4 roots are well, u1 is minus root of u plus 2 lambda squared. P2 is minus root of u minus 2 lambda squared. P3 is plus root u plus 2 lambda squared. P4 is plus root of u plus 2 lambda squared. Okay, so this curve determines y as a double cover of the x plane. You can solve for y. There is a square root of the right hand side. Okay. And this double cover is branched at the roots of the right hand side, E1 and 2, E3 and E4. Okay. And well, again, I mean, since X is a complex plane, you can view this as a Riemann sphere by adding quantity infinity. Okay. So pictorially, what we have is that so we have 2 sheets because y is determined in terms of x by a square root type formula. So I have let me first draw the x plane, and here are the 2 sheets. So on the upper sheet, y is equal to square root of product x minus pi. On the lower sheet, y is equal to minus square root product x minus pi. And we have these branch points, let's say E1, E2, E3, E4, and let's draw the cuts as follows. E1, E3, E4. Okay. So as we cross the cut, we go, say, from the upper sheet to the lower sheet. So in fact, this the cut here is identified to the cut over there. So you should think as these 2 cuts as being identified. And now, if I mean, sometimes if you compactify the x plane to a Riemann sphere, so here you have something like a Riemann sphere up there, a Riemann sphere down here, and then we have some identification, which is looks like this. And so now this, so you should see that it looks like a torus, no? Introduce the handle by this identification. And then we have this alpha and beta cycles, so let me try and draw them. So I guess I'll pick so we can take the alpha cycle to go like, okay, so the way I've drawn this is like this. So if you turn your head 90 degrees, this would look like that. So it takes a little bit of imagination, but it's not too hard. So we're gonna have the alpha cycle will go like this, and the beta cycle goes like this, and now here it crosses the branch gap, and it goes back down there and closes like this. Okay. So if you would connect it. Okay, so in the following, rather than drawing the two sheets of this double cover, I will draw just one sheet, so the complex plane, the x plane once, and I will use dashed lines for paths which go in the lower sheet. So let me redraw this picture in that way. So we draw. So here, say we have the E plane, the X plane, E1, E2, E3, E4. This is the beta cycle. And this is the alpha cycle. Okay, and then because the X plane is a Riemann sphere, you can actually deform cycles. In fact, this cycle here is also the alpha cycle. And with a little bit of thinking, I can explain later. You can see that also the counterclockwise cycle in the lower plane. This is also the alpha cycle. Okay, this is just you can understand it just by deforming that path and maybe going from the upper to the lower sheet. Okay, trust me, for now I can explain more detail privately. Okay, so we've chosen a basis alpha and beta of one cycle. So this is some canonical homology basis. For the first homology group of these curves. And we have an intersection pairing which tells us how the various cycles intersect. So in particular, alpha, and I will note this intersection pairing by this circle. So the self-intersection of alpha is 0 because you can deform alpha. Say, I don't know, take this representative of alpha and that representative. You don't intersect. Same thing for beta. But on the other hand, alpha and beta have a non-trivial intersection. And because these are one cycles, in fact, the orientation matters. And so this intersection number is anti-symmetric. And I will stick and normalize like this. So here alpha and beta intersect only once, and the right hand side is positive because you go from alpha to beta by positive rotation. Okay, so next I told you that we want to identify the complexified gauge coupling of the infrared effective theory with the complex structure parameter of these two torus. Okay, so let me explain how this complex structure parameter is computed from this form, this algebraic form of the two torus. So again, so the low energy coupling tau as a function of u is complex structure modulus for a period matrix of xu. And so how is this complex structure modulus of the two torus computed? It's computed as follows. So first one introduces a holomorphic differential So it's a holomorphic 1,0 form, and essentially the space of holomorphic differentials on a torus, say on a Riemann surface of genus G has a dimension G on torus, there is a unique one, again up to multiplication by a constant, and in this case can be taken as follows. So this is really holomorphic on the Riemann sphere on the closure of the complex plane. So you can in fact check, this is a good exercise. Check that omega is indeed a holomorphic that has no singularity, but it's regular everywhere on the Riemann sphere for X. So since omega is given by dx over y of x, where y of x is one of the two solutions of the Seiberg-Witten curve, so there are some dangerous points like you might worry that x equal ei are dangerous points because there are zeros of y, and also x equal infinity are dangerous. But okay, it's a good exercise to check, to plug in x equal ei or x equal infinity, change the variable, say, to 1 over x, and you can see that this differential is really regular. Okay, so there is this holomorphic differential on the two torus. It's the only holomorphic differential that we have up to multiplication by a constant. And the complex structure parameter or period matrix tau of the torus, which for us would be a function of u, is given by the integral of this holomorphic differential on the beta cycle divided by the integral of the holomorphic differential on the alpha cycle. Okay, and then there is a mathematical identity called Riemann's second bilinear identity, which in fact is quite easy to derive, but I will not do it here for in the interest of time, which guarantees that the imaginary part of tau is positive, which for us was crucial because this is the condition imposed by unitarity. And okay, so this is positive for a regular torus. If the torus develops a singularity, the imaginary part can go to zero. Okay, so this is on the geometric side. But physically, we remember that we derived the formula for the effective complexified coupling, which we want to identify this complex structure of the torus. A formula which is given in terms of the special coordinates. So physically, we have our formula for tau of u that is given by the derivative of a dual of u with respect to a of u. Okay. So in particular, we can rewrite it as the derivative of a dual with respect to u divided by the derivative of a with respect to u, where u is our global coordinate, the coordinate on the Coulomb branch. Okay. So this is on the physics side, and this is on the mathematical side. So we'd like to equate the two expressions. And so in particular, so you can infer that the derivative of a dual with respect to u is given by the integral the so-called, well, I should say, I mean, these objects are called periods. These line integrals are called periods of omega along the beta and alpha cycles. So by equating this mathematical expression to the physical expression, you can infer that the derivatives of a dual with respect to u is proportional to the period of omega along beta, and similarly, the derivative of a with respect to u is proportional to the period of omega, the holomorphic differential along the alpha cycle. Okay, in principle, you might imagine that there is some function here in front, some function of u that cancels out and when you take the ratio. Okay, but essentially, so first of all, we don't want a function here because this function will essentially introduce some extra singular unwanted poles or zero. Okay, so the function actually must be a constant. And okay, essentially you can fix this constant by choosing the normalization of the holomorphic differential, which you can choose at will. Okay, so this expresses the derivatives of the special coordinates with respect to the modulus of the Coulomb branch in terms of periods of the holomorphic differential. But to compute, say, central charges and some masses of BTS objects, we actually want a formula which expresses a dual and A as a functions of U. Okay. So what we're going to do is integrate these equations. By introducing another differential lambda, okay, such that the derivative of lambda with respect to u is given by, well, let's set the coefficients 1, is given by omega. Okay. So this differential lambda is called the Seiberg-Witten differential. So unlike omega, which was holomorphic, lambda, the Seiberg-Witten differential, is actually meromorphic. So in particular, it has some poles. So it has poles, but one can see that, at least in this case, it has no residue. Mathematically, it's some abelian differential of the second kind. We know what that is. Anyway, so this is a differential. And okay, maybe the other comment is that this differential is defined up to some exact form, exact piece, okay? Because we only care about its periods, so about its integral, line integrals over loops. Okay. So in this case, the differential, the meromorphic differential which does the job, in the case of SC2, using this parameterization of the curve, can be written, for instance, as follows: 1 over 2 pi I, 2x squared dx over y of x. So there are many equivalent descriptions which either differ by, say, exact pieces or, I don't know, changes of variables, but I guess you can stick to this form. Maybe I can add also another form, which is sometimes useful. So it's dx arc wash. So again, here, since lambda is determined up to an exact form in all the relations which involve lambda, they all hold up to an exact form. So here, there is always this ambiguities. Okay. And you can check that the derivative of lambda with respect to u gives indeed this holomorphic differential up to irrelevant exact forms. So the other thing that you can check is that, so as I told you, this is a meromorphic differential, it's not holomorphic. In particular, it has a double pole at x equal infinity. So this is a double pole, so there is no residue. Okay, so we've deduced a prescription to compute a dual and a, our special coordinates, as functions of u, the variable on the Coulomb branch. And in particular, from this, you can also deduce the prepotential by integrating these two expressions. Okay, so we need to check a few things. To see that this gives us the solution of the problem of determining the infrared effective action. So, okay, so first of all, we want to check that the Seiberg-Witten curve xu degenerates at the singularities in the U-plane, so xu degenerates at u equal plus minus lambda squared infinity, and it degenerates in the appropriate way. Second, we have to check that a dual and a have the correct asymptotics around the singularities. Which in particular they have the correct monodromies. So if that's the case, so we have found the solution to our problem. Okay? So we determined a dual and a as a function of u, which satisfies all the properties that we wanted, and it agrees say with the coupling computation, it has the right monodromies, and so on. So I'm again, in the interest of time, and since maybe this particular form of the Seiberg-Witten curve is not the best form to do that check, I will not check that the asymptotics at u equal infinity is the right one, but this is the next slide that do. And anyway, so what we're going to do is to first look at the singularities of this Seiberg-Witten curve, and then check that it has the right monodromies at the monopole and dion point. Okay, so singularities. So as I told you, so the picture here is that the Seiberg-Witten curves gives the torus in terms of some branch cover of the x-plane, the branch points E1, E2, E3, and E4. Okay. So if the branch points are all distinct, then the torus is regular. But on the other hand, the torus is going to become singular when two branch points collide. Okay? So that corresponds to geometrically to the fact that one cycle vanishes. So maybe I should draw again various cycles. Hopefully I'm using the same colors as before. Which color did I choose for the alpha cycle?
Orange.
Orange. Okay. Okay, so this is alpha. And this is beta. Okay, so so these singularities will occur for special values of u, and these special values of u can be obtained by looking at the discriminant of this equation. So these are correspond to the vanishing of the discriminant. Let's call it discriminant delta. This discriminant is just given by the product of pi minus pj squared, I is smaller than j. This is the definition, so it will vanish when two roots coincide, two branch points coincide. And if you apply these simple formulas, it's an exercise to see that this is well, up to constants, I will not bother to write. Is equal to u squared minus 4 lambda to the 4th. So let's look at this zeros of this discriminant. So this is a, or maybe I should determine from. So in particular, one of the zeros is at u equal to lambda squared, which was the monopole point. So when u goes to 2 lambda squared, what happens is that E2 and E3 both go to 0. Okay. So these two branch points collide and the beta cycle vanishes. Let's call this cycle nu of 2 lambda squared. This is the cycle which vanishes when u is 2 lambda squared. And in particular, because the beta cycle vanishes and tau was given by period of omega along the beta cycle divided by the period of omega along the alpha cycle, this will correspond to tau equals 0. So similarly, we have another 0 at u equal minus 2 lambda squared that we identify with the dion point. So in that case, E1 and E4 will both go to 0 and will collide. And okay, maybe we're gonna see, maybe not, see that the cycle which vanishes here is beta minus 2 alpha. And that implies that tau goes to 2. Which remember was one of the clasps in the fundamental domain. Okay, maybe I should explain why beta minus 2 alpha vanishes. In this case, it's clear that if E1 and E2 and E3 collide, the beta cycle vanish. Okay, it might be slightly harder to see why beta minus 2 alpha collapse when these two branch points collide. So let me try to draw it on the board. Okay, so let's. Oh. So this is the alpha cycle, and by the formation I told you that also this other one is alpha. On the other hand, the beta cycle looks like this. Okay. So let's first try to construct beta minus alpha next to construct beta minus 2 alpha. So this second cycle here will remain as a spectator, you know, and I guess. So we just want to add to beta the opposite of alpha. Okay, so let's say that we start from here. So now we want to write beta minus alpha. So we start from here, then we reach this point. Now we go along minus alpha, so which is in this direction, and then back here. Okay, so next we continue, and this is the cycle that we get. Can you see that? Should I do it again? Again, or maybe you can see it. Okay. So then alpha cycle looks like this. In particular, we now want to add to subtract alpha again. So let me draw at this point minus alpha. So minus alpha will go like this, and then I guess it's convenient here to deform it in this way. Okay.
So, question.
Yes.
Why? So when we follow beta, we cross alpha, then we follow alpha, but then we cross beta again. Why don't we?
So what I've done here was to, well, okay, let me draw minus alpha, which goes like this.
Yeah.
So what I've done was just to deform like this.
Yeah, but why not the second cross?
Not here.
No, the left hand side. Below.
Because here, I mean, the dashed line is in the second sheet and the solid line in the first sheet, so we have to be in the same sheet. Okay, so now I want to add to this cycle beta minus alpha, which I found, this other cycle of alpha, and so okay, we can do it again. So in particular, so let's start from here, I guess. Okay, so now we end up at this point. So what I'm gonna do is to deform like that. Okay, so I'm following this path. And then back like this. Okay, so now this is beta minus 2 alpha. Okay, if you don't see it, I can try to do it again later privately. Not easy to do it on the board. If you believe me, okay, and then you can deform this path, but this path will collide. This path will vanish when this point and that point collide. I mean, essentially, we should rotate this and that, and then go back to that situation. We can do it slowly later in private. So anyway, the point is that at the Dion point in modular space, this cycle vanishes. Okay, I should also say that there is, in a sense, that there is an extra singularity at u goes to infinity, where, okay, the discriminant doesn't vanish, but some dimensionless version goes to 0, and this corresponds to tau going to I infinity. In that case, there is, strictly speaking, there is no cycle which vanishes. But so this essentially is going, so when u goes to infinity, essentially, U is much larger than lambda, and so roughly speaking, E1 and E2 are comparable. So if you work in dimensionless variables, you'd say that E1 and E2 collide. Okay, so we found the singularity, so now let's check that the monodromy is at this point, and the second point at this point is exactly the monodromy matrix that we found for massless monopoles, and here the monodromy matrix that we found for massless dyons. Okay, so let's consider the monodromy at U equal to lambda squared. So, okay, so what we do is we send U minus 2 lambda squared to e to the 2 pi I U minus 2 lambda squared. So, and this operation in particular exchanges E2 and E3, okay? Because it exchanges the two square roots. So we'll see that this exchanges E2 and E3. Whereas E1 and E4 remain as spectators, and particularly what this does is to send the beta cycle, to keep the beta cycle as it is, and send the alpha cycle to alpha minus beta. And remember, beta here was the vanishing cycle. So the vanishing cycle remains the same, it's invariant, and the other cycle changes. Okay, so now let me draw another picture to try to see, to show that this is the monodromy. So we only have to focus on E2 and E3. So I'll say this is E2 and this is E3. And maybe this is the beta cycle. Whereas the alpha cycle goes like that. So what we want to do is that, so we follow this monodromy which exchanges E2 and E3. So E2 will go this way, E3 will go that way until they're exchanged. Okay, maybe, so let's do it in 2 steps. So let's first do half the rotation. So if you do half the rotation, E2 is here, E3 is there. So then the beta cycle still encircles both of them, and the alpha cycle started from here and then must go this way. Okay. So next we do the other half rotation. So E3 goes here and E2 goes there. So the beta cycle doesn't care about this, it still encircles E2 and E3, but the alpha cycle goes like this. Just by following the deformation. So the new beta, beta cycle remains itself, so it's invariant, whereas the original alpha cycle became this new cycle up there. Okay, so this, I call this alpha nu. So now let's forget beta. Okay. So this alpha nu is equal to the original alpha cycle, alpha old, plus this loop here. And now, okay, if you follow the deformations, you can let me draw again the comments here. So I'm looking at this extra bit, we can deform it like this. now because I mean we're interested in integrating lambda, the meromorphic differential has no poles at the branch point, so these two small circles around the branch points will not matter, and this extra beta is also equal just to minus the old beta, because it goes around the two cycles like this. Again, I invite you to try yourself. I mean, it's easy to get confused with these pictures. I can help later if you don't buy them. Okay, so I said this is the, so we derive that this is the monodromy, and we can view that as a transformation on beta alpha, and they go to new beta cycle and new alpha cycle, given by 1, 0, minus 1, 1. Okay. So notice that this monodromy matrix is nothing but the monodromy matrix that we assign to a monopole, massless monopole, magnetic charge 1, electric charge 0. So we deduce also from here that monodromy matrix around the singularity 2 lambda squared is takes this form. So now I'm going to get to monopoles and dyons in a few minutes. So you can repeat the same exercise at the other singularity. Essentially, this is obtained by which exchanges E1 and E4. You can obtain this from the previous result by just sending replace beta vanishing cycle with beta minus 2 alpha, where alpha remains. And you'll find that the monodromy matrix around this singularity is minus 1 or minus 1, 3, which is nothing but the monodromy matrix that we found for a dion, magnetic charge 1, electric charge minus 2. Okay. So in general, what we're seeing is the following correspondence. So we have the singularities. This physically will correspond to having some massless hypermultiplet of charges and we are associating this with a vanishing cycle mathematically of winding numbers m and n. Okay. And finally, we associate to the singularity monodromy matrix, which physically is determined by the charges of the hypermultiplet, which become massless, and physically and mathematically by the winding number of the cycle, which vanishes. So this correspondence between the massless hyper and the vanishing cycle is what I haven't made precise yet, and it goes as follows. So this is essentially just due to the central charge formula. So we use the central charge formula, and the fact that the dual special coordinates are given by integral of the Seiberg-Witten differential, this meromorphic differential lambda, either on around the beta cycle or on the alpha cycle. Okay. So let's consider a cycle mu of winding numbers m and n. So we can write this in these terms. So then you will remember that the central charge formula for a dion of mass of magnetic charge m and electric charge n was magnetic charge times a dual plus electric charge times a, which is also equal to mn times a dual a. Okay. So now if we use the prescription to compute the special coordinates, this is nothing but mn times I guess the integral of lambda either over beta or over the alpha cycle. So the central charge putting these things together, we see that the central charge of a dion with magnetic charge m and n is nothing but the period of the holomorphic Seiberg-Witten differential lambda over the cycle nu equal to m beta plus n alpha. So whenever the cycle with winding number mn vanishes, the dion with charges m and n becomes massless. And so, and in particular, with this also allows us to encode the monodromy for either the charges or alpha dual for a dual and a in terms of the transformation laws of the cycles. Okay, so let me take maybe 5 minutes to add one last thing. So remember, so here I've used a specific basis of homology cycles, alpha and beta, but you might choose another basis, and two different bases are related by symplectic transformation, which is SL to Z transformation. And that translates on the physics side to the change of basis of homology cycles, beta and alpha, corresponds on the physics side to a change of electric magnetic duality frame. So it's an electric magnetic duality transformation. So if you rotate, remember that that is kind of a passive transformation. So you rotate the cycles of, say, a dual and a, and rotate m and n oppositely, so that the central charge changes. Doesn't change. And indeed, what is invariant? I mean, it's up to you to choose basis of the homology cycles or electric magnetic duality frame. What is important are physically and also mathematically are invariant objects. So in particular, what is invariant is say the intersection number mathematically. And so let's just check what the intersection numbers is. So this is n, say m1 beta plus m1 alpha intersection m2 beta plus m2 alpha. And if you use the intersection form, so beta intersects alpha with minus sign, so this is minus m1 m2, and then alpha intersects beta with plus sign, this is plus m1 m2. So the invariant information under changes of homology cycle, which is the intersection number, translates to the Dirac pairing of electric and magnetic charges, which is also what is invariant under electric magnetic duality on the physics side. So also maybe let me just mention, without explaining, that there is a simple general formula which allows you to compute the monodromy matrix associated to a vanishing cycle, which is called Karl-Lefschetz formula. So this gives a monodromy associated to, let's call it m nu associated to vanishing psi of mu. And the formula is given like this. So it takes any one cycle gamma and then maps it into m mu gamma, which is equal to gamma minus gamma intersection mu times mu. So if you use the formulas for the intersection numbers, like before, you can do the exercise and check that if mu is mn times beta alpha, so if the cycle mu has one number mn, then this m mu is nothing but the monodromy matrix for associated to a massless dion with magnetic charge m and electric charge n. Okay, so I see that I'm out of time, so let me just close here. Maybe I should mention that okay, the formulas that I given, I mean the prescription that I've given for determining following Seiberg-Witten for determining a dual and A are given as integrals in terms of integrals of meromorphic differential lambda. In the case of the SU2 gauge theory that we consider here, in fact, these integrals can be computed quite easily. They're given in terms of some called elliptic integrals, and they can also be replaced in terms of hypergeometric functions. So you can actually go and find quite explicit expression for the values of the special coordinates A dual and A as functions of U. And you can also then go back and try to expand this expression for A dual and A as a function of U. And you can do an expansion in three patch. One is the expansion in the patch at infinity, and you will reproduce the asymptotics at small coupling at large U. And by following the expansion, you can compute all the coefficients in the instant interactions. And similarly, you can do the same exercise in the patch close associated to the monopole singularity, or the patch associated to the dion singularity. And in that way, you can recover not only the logarithmic terms in the asymptotics, which govern the monodromy, but all the instanton corrections, or all the corrections into massive states. Okay, I mean, there would be many things to say more than this, but let's stop here. Thanks for your attention. Okay, any questions? I was planning to say something about the curve of marginal stability, but okay, if anyone is interested. So that tells you what happens to the spectrum of BPS states as you move along the Coulomb branch. Well, let me just mention that it turns out that there is a curve which looks like this. So the Coulomb branch looks